All right, so in the intro to this lesson, so the lesson 2 intro, I explained that we're going to be talking about the concept of differentiability, and that differentiability has something to do with our ability to take the derivative. In fact, if I were to define the word differentiability, I would say the ability to take the derivative. So that's pretty easy. That we can understand what that means. In other words, we could use the formula that we talked about in lesson 1 and we could find a derivative. However, as it turns out, just like anything we've been talking about, there are some limitations in graphs to what we can analyze based on the nature of those graphs. And I maybe shouldn't even say graphs, really the function itself, but we often can visualize what's happening with a function based on its graph. So let's look at this blank sheet over here, and let's clear our lower third. In order to be able to differentiate something or take the derivative, it means that we're able to find the instantaneous slope at that point. And so let's say we have a graph like, let me change my color here, like x cubed, which we talked about in the last lesson. And we said we can actually find, we used our formula for taking the derivative to find out that if f of x is x cubed, then f prime of x, or the function, the derivative, the function that will give us the instantaneous slope at any point along x cubed, is 3x squared. So I'm just copying that information from the prior lesson, and if you look back in your notes, you should see that. What that means is that this function is going to show me what that derivative is at any of these points. And it makes sense that anything along this curve of this function, but we can also call it a curve, is going to have a slope. The only thing that might come across as a little tricky is that right here at the center, there's a slope of 0. So that might be the one thing that looks a little bit interesting or different. But every other point along here, it really doesn't take too much of a stretch of the imagination to assume that those points have slope, and slope that is changing as you move along that line. Okay, however, it is possible for me to create graphs or functions that do pass the vertical line test of being a function, but don't have that nice smooth shape that would allow me to find the slope or the derivative at each of those points. And let me give you a couple examples. Let's say that I had a function that looked like this. It probably would be a piecewise function. So maybe it's coming along, it looks just like our cubic function does. And then instead of moving upward like this, it goes like this. It's coming up, 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 and then just has this really sharp corner and turns down. Would we assume, so just in case you're having a hard time picturing this, I'm imagining that I'm drawing a function on a graph somewhere. Oops, it's harder than I thought to retrace that. So here's our function. It's coming up, 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 and then it has a sharp downturn and moves on down. Is that a function that's differentiable? Well, everything looks pretty normal, like I could find a slope at a point here, except for this little thing that we call a corner. How can we define this corner as having a slope if, as we're coming up from the left-hand side, I have a totally different shape than what's happening down the right-hand side? And if that kind of is a thought that's going on in your head, you might be onto something. Let me give you another example of something that would fall into this. And let me quickly just erase this section here. Clear it out. Okay, so let's say that we want, I want a green color here. Here's our graph. And I have a function that's going along like just curving up here, just like the last one. Coming up, it's fine. And then all of a sudden, right around here, it just jumps. We have what we call a jump discontinuity, and then carries on the graph from there. Is that a function that is differentiable at all points? Well, again, we're asking ourselves, do each of these points on this graph have a derivative? Do they have a slope? Well, I have no problem believing that any point along this line is going to have a slope, an instantaneous slope at each of those instantaneous points. And even at this part, which kind of maybe is a line or close to a line, all of those points look like they could have a slope, even if it was 0, because if it flattens out, then yeah, it would have a slope of 0, but still that's not a problem. But right here at this corner point, here and here, we might ask ourselves the question, how can you find the instantaneous slope of a point that only has something happening either on the left or on the right? Like, there seems to be some information missing here. And again, if that's something that you're thinking, you might be onto something here. Because if we're moving along and then at an instantaneous point we jump, we're creating a big question mark as to what the slope is at that point where it jumps. Now, we might be able to define a slope coming from the left, or we might be able to define it as having a slope coming from the right. This should remind you of something like continuity. Remember we talked about that? We can have continuity or we can talk about limits coming from the left, and we can talk about limits coming from the right, but if there's a disjointed section, in this case a jump discontinuity, we can't really define it as having like one answer. We have two different answers at that point. Okay, one last possible issue that we might want to consider. And again, let me erase this so we have room. So we talked about something that has a corner, or we also can call it a cusp. If it's kind of, so if it comes up like this, that's a corner. If it kind of looks like this, it would be a cusp. Like, so it's kind of rounded, but then it comes to a point. That's a cusp. Or we can talk about places where there's discontinuity, like there's a jump or there's a piece missing, something like that, so discontinuous. The last big question mark for us is something like the cube root function. So we talked about the cubic function up here, which is why I want to leave it up there. But the cube root function has this part that goes vertical, essentially, and then keeps on going. As a function, this is not a problem. It does pass the vertical line test, meaning there's no repetitions. Even at this point where it appears to go vertical, it doesn't have a repetitive point, so it still passes off as a function. However, we're not talking about the function itself right now, or the position of the function. We're talking about the slope of the function at each point, and can we define there being a slope at each point? Well, all along this part here, and all the way up, and then from this beginning part here at the origin, and so on and so forth to the right, I have no problem assuming that there should be an instantaneous slope at each of those nice smooth points. However, at this one little point in the middle, it appears that the graph goes from moving kind of in a horizontal position to a complete vertical position, which is in slope, in the world of slope, we call that undefined. We don't talk about slope that runs straight up and down. Now after that, it moves back to a horizontal position or a diagonal to horizontal position, and that's fine. But again, if something inside you feels like that point right there in the center doesn't look like it has a numeric slope that I could label, you are onto something. There is something true to what you're feeling there. Okay, so what have we discussed here? We've discussed that there are many ways that we can find slope of instantaneous or infinitesimally small points along a curve. However, if we have a corner, if we have a cusp, which is basically a corner that's just rounded, or if we have some kind of discontinuity, or if we have the problem where for an infinitely small moment in time, the function actually turns completely vertical, then we are creating points that are not differentiable. That means there are points, maybe just one, along this function where we can't find the derivative, we can't find the slope. That means the whole function, we would call it not differentiable. We could select a part and say like, oh, from 1 to 5, it is differentiable. But the function as a whole, we cannot call differentiable. So if you're looking for a definition, that's what it is. Differentiable means that I can find the slope of any point on the entire function, or that I can find the slope of any point along a certain interval. Why is that important? Why are we discussing this? Well, as it turns out, well, first because we're talking all about derivatives, so knowing whether or not we can take the derivative is certainly an important thing to know. But it's also important because just like, remember we talked, let's go to this blank sheet. This is one of those things I want to show you rather than tell you. Remember we talked about continuity, and we said if there's a point over here, we'll say it's at x1, and there's a point over here, we'll say it's at x2. Each of those have y values. We'll call it y1 and y2 just because why not? It seems to make sense. So we have these two x values. If and only if I know that this is a function that is continuous, write that out. If it's continuous, then I can safely make the assumption that this graph, no matter how either boring and straight it is, or crazy wiggly up and down it is, if it's a function and it is continuous, then every single y value between y1 and y2 is going to be hit at least one time by the function. And we call that the intermediate value theorem for continuous functions. And that's something we covered in the previous sections. Okay, think about that same idea and let's apply it to derivatives, and specifically the concept of differentiability. So let's say we have a function, we're going to call it f of x, and let's say I know for certain that between some point, we'll call it x1, and some point x2, this function is differentiable at all points. So between x1 and x2, it's differentiable. So there's no corners, there's no cusps, there's no breaks in the graph, some kind of discontinuity. There is no place where it turns vertical, even for an instantaneous moment. Then I can safely make the assumption that the derivative, so we'll say f prime of x, exists at every single value between f prime of the first point and f prime of the second point. Same exact logic that we used in the intermediate value theorem for continuous functions. This is called the intermediate value theorem for derivatives. And it basically is the same as continuous functions. If you can set parameters for where it's differentiable, then you can also know that all the derivatives exist within that range. And that is going to be a nice, helpful assumption that will carry through into some of our further proofs and work. That is it for lesson 2. It's all kind of theoretical in this section. We didn't actually have to do any real like algebra calculus work. I mean, I guess it's calculus work, but we did a lot of talking rather than a lot of writing. And that's okay. Just make sure that you have those key points written down, and you can turn off your computer and you are done for the night.